What is up, guys? Today we're going to be looking specifically at a certain part of the whole process of a respiration and energy generation. And we're going to be looking at the electron transport chain, specifically looking at the mechanism by which it's able to generate ATP using the NADH and FADH2 produced from glycolysis and the Krebs cycle. But we're also going to look at some of the cofactors that are needed for some of the transporters of the electrons to go from the different complexes, along with various drugs that affect specific parts of the complex. And I'm going to be using various mnemonics throughout this to help make all of this a lot easier. So let's get right into the video. This is an overview of just the complexes and their names. So this is really important. I haven't seen too many other videos really dive too much into the names. For example, complex 1 also is called NADH dehydrogenase. Complex 2, succinate dehydrogenase, and then so forth. These are really important because on a board exam, they may not just call it complex 1. They could call it NADH dehydrogenase or any of these other ones. And then if you look at complex 4, it's called cytochrome A plus A3, or it could also be called cytochrome C oxidase. I'm going to show you mnemonics to help you remember the majority of these so that it becomes easy to kind of recognize the names and link them to the complex numbers. Okay, so let's move forward. This is just a general setup of basically the mitochondrial inner membrane, which is where the transport of protons and their electrons are going to be happening. So you need to know, first of all, that this inner part of the mitochondria is called the mitochondrial matrix. That's the very inner part of the mitochondria. Then this is going to be what's called the inner membrane. Okay, the inner membrane. And then the inner membrane separates the matrix from that part outside of that then, which is just going to be, so this would be called the inner membrane space. The reason this is called the inner membrane space is because actually this is the inner membrane that I've put an arrow to right here, but there's another membrane out here, which is the outer membrane, but because it's not really involved too much with the electron transport chain, we're going to focus on just the inner membrane space, the matrix, and then the inner membrane that is between the two. All right, so let's try to simplify some of this. So first of all, this is complex 1, complex 2, complex 3, complex 4, and then complex 5. Okay, so now let's get into the very beginning of this. So we've gone through glycolysis, we've gone through Krebs cycle, and we have generated various NADHs, and then FADH2s. So these basically harness energy. So I'll just put, because there's more than one of these of each. So we've basically harnessed energy within these protons that are within the protons and the electrons that are within these NADH and FADH2. So the first thing you need to know is we're going to start at complex 1. Complex 1 is called NADH dehydrogenase, and I'm just going to abbreviate it, dehydrog. This is NADH dehydrogenase. Now, how do you remember that this is going to be called NADH dehydrogenase? Whenever I look at the N and the NADH, I just tell myself this is referring to something new. In other words, new is referring to this is the very first thing that we're going to do. This is the brand new thing in this pathway. So new helps me remember that this is the very first complex. It's called NADH dehydrogenase. Now, just like its name, this is why another reason why it's important to know that it's called NADH dehydrogenase. Just like its name, well, what is it dealing with? It's dealing with only the NADH. This is very high yield. It's not dealing with the FADH2. We're going to learn later on that complex 2 is where the FADH2 will go. But to begin, the NADH is basically going to help to activate. It's going to basically activate complex 1 by sending its electrons to complex 1. And when this becomes activated, or you could say charged, it's going to force a lot of protons that are here in the matrix through complex 1 and forcefully send them into the inner membrane space. So we have tons of hydrogen ions now in the inner membrane space. Now, it's going to stay activated for some time, but after it's basically forced enough of these hydrogen ions, these protons, over into the intramembrane space using NADH's electrons that came from it, what's going to happen is this electron that has activated this will not go to waste. It will then attach to a transporter called CoQ. Okay, it's going to attach to CoQ, to CoQ, and then CoQ is going to move on basically to complex 2. So it's going to now assist in complex 2. Okay, so now what's going to happen? You're going to, in complex 2, it's involving FADH2. So let me basically clear all this up to make it neat. So now we're at complex 2. We've gotten these hydrogen ions that basically were forcefully pumped through using the activation of complex 1 using NADH. Okay, how do we remember it's NADH? Because the N in the title, NADH dehydrogenase, which is what it's called, starts with an N, and that makes me think of the new, kind of like a new starting point. So this is the starting point, complex 1. Now we're going to look at FADH2. And don't forget, the electrons that activated this that came from NADH are going to go on to CoQ, coenzyme Q, and CoQ is going to carry that over basically, and it's going to kind of wait right here. So now, basically now what's going to happen is FADH2 is going to do the same thing. So before we get into that, let's look at what complex 2 is also called. So also complex 2 is also called succinate dehydrogenase. Now, how do we remember that? Because remember, on an exam, they may not tell you complex 2. They may be referring to complex 2 and call it succinate dehydrogenase by its full name. Whenever I look at the S in succinate, I think of second. Like the second complex, and that's what it is. It's complex 2 for the second complex, succinate dehydrogenase. Okay, so this is going to take the electrons from FADH2, and it's going to, but this one's different. It is not going to pump hydrogen ions like what happened over here in complex 1. It is only going to take the electrons from FADH2, basically charge this complex up, but then that CoQ that came from complex 1, it is going to attach on. All of those electrons are now going to attach to the CoQ that came from 1, and they're going to go ahead and move on over to complex 3. So it's just taking the energy, but complex 2 doesn't necessarily act as a proton pump into over here, which is going to be the intermembrane space here at the top. Okay, so we have all of these electrons that came from NADH and FADH2, and we've generated some protons from complex 1, and now we're moving into complex 3 with that coenzyme Q that's bringing all of those electrons. So now, what is going to happen in complex 3? First of all, we need to know the name of complex 3. The name of complex 3 is cytochrome BC1. Now, I don't really have too much of a clever way to remember this one, other than when I see cytochrome, that starts with the C, that's the third letter of the alphabet, so you could say that's complex 3, but you'll see that that's very similar to complex 4 when we get to it. So I just use the fact that it has a C here, and it also has a C here. So the two C's can maybe help you remember that complex 3 is called cytochrome BC1, just kind of a thing to help recognize it when you get to a multiple choice question, if it's in the choices. So this is called complex 3 or cytochrome BC1. We've already sent the NADH to complex 1 and the FADH2 to complex 2. We've gotten all of the electrons, attached them to CoQ, which was going from 1 to 2, and it's now taking all of those electrons and it's going to activate complex 3. Now, complex 3, when active, it's going to act just like complex 1. It is going to basically pump all of these protons across into the intermembrane space, so that now we'd have more of kind of an electromotive force. And so there's a lot of a positive charge building up all here in the intermembrane space that used to be down in the matrix, and now it's moving into the intermembrane space. Okay, so just like we said before, we gave the name, this is complex 3, it's sending electrons across. It's not sending electrons across, it's sending the protons across using the electrons from coenzyme Q that came from complex 1 and 2, from the NADH and the FADH2. So now that we've gotten more protons, we need to take these electrons, and we need to now coenzyme Q has done its job. it has basically carried the charge, the electrons from 1, 2, and now when it reaches 3, it's going to pass its electrons of all of that it's carrying. It's going to pass it to a new transporter, and the transporter is called cytochrome C. That should make sense. Look at the title of look at the name of the complex 3. It's cytochrome BC1. So naturally, cytochrome C would be the most logical name for a transporter that's now moving all of the electrons that came from coenzyme Q, and that's now on complex 3 is going to attach to cytochrome C, and it's going to be transported to finally complex 4, and let me go ahead and write complex 5 here for when we get to that. So now we're at complex 4. Complex 4 is called cytochrome A plus A3. Now this is where a mnemonic makes the most sense here, because there's a lot of things you need to know for what happens here at this complex. It also goes by another name, but I just remember cytochrome A plus A3, and then you can get everything else. Let me show you how. Cytochrome A, so you're basically taking, just read it, cytochrome A plus A3. Cytochrome basically is saying 1A plus 3 A's is 4 A's, is it not? Well, there we go, complex 4. So 4 A's have gone into this, so cytochrome 4A, and that should help you remember this name is involved, is another name for complex 4. Now, also, just like we said that this is cytochrome that has 4 A's, I just want you to help that then to remember this. The 4 C's of cytochrome A plus A3. The 4 C's of cytochrome A plus A3. This is the mnemonic. And we're going to start with the other name this goes by. So this goes by another name, and the name it also can go by is cytochrome C oxidase. Look at the beginning of this. Look at the middle part of this. Cytochrome C, CC. So that's our first C. Let's go to our second C. What else is involved with this? The next thing that's involved is copper. Copper is needed as a cofactor in complex 4. The way you remember that is because cytochrome A plus A3 should help you remember we're dealing with 4 C's of cytochrome at complex 4. The 4 C's. So we have cytochrome C oxidase, which is the other name besides cytochrome A plus A3, and we have copper that is needed as a cofactor to run this, this complex 4. The next thing, a drug that works, 2 drugs that affects this specific complex. The first one is carbon monoxide. There's our C in this one. And the very next one is going to be cyanide. Both of these affect complex 4 in slightly different ways, and we won't get into too much of the details of that, but notice that the 4 C's have helped us in generating all of the information we need to know about complex 4. And complex 4 is going to do the same thing that complex 3 did, the same thing that complex 1 did. Remember though, complex 2 does not pump protons through. It just basically has the electrical charge to pass on into coenzyme Q. So complex 4 is going to react just like all of the other main ones. It's going to send protons over here, and we're generating more and more of a positive charge from all the protons and an increased electromotive force. All right, finally we get to complex 5. I should just write it like this. I don't know if I should put 2 lines above it. So this is complex 5, and this is just going to be the ATP synthase. The reason I don't have a mnemonic to remember that this is called ATP synthase is because complex 5 is the end. It's the final complex, and you should know, if you can just remember, the point of electron transport chain is to generate ATP. That should make sense that the final thing after going through all of those annoying complex steps is to make ATP, and it's going to convert ADP to ATP using all of these protons that were pumped all throughout the different complexes 1, 3, and 4, and it's going to now send them back through. That's going to generate a lot of basically potential or power to be able to generate the conversion of ADP to tons of ATP, and that's our final goal. Now, I've said all that, but I haven't truly finished with the drug part. The only reason I talked about these 2 drugs affecting complex 4 is because it was part of the 4 C's of cytochrome A plus A3. Now let me clean all this up and let's get into the drugs. So let me go ahead and jump right here because we already talked about 5. So I'm going to go ahead and just write in complex 4s. We know carbon monoxide and we know cyanide, and we know that because of the 4 C's of complex 4. So those 2 basically inhibit complex 4 and shut down the electron transport chain. Now there's some other ones. There's one at complex 1, and it's called rotenone. I hope I'm pronouncing that correct. This is really simple to remember. This is at complex 1. Let's look at the word. Rotenone, roten 1. It affects at complex 1. It inhibits complex 1. The other one that we're going to look at is called antimycin A. Antimycin A. Now, I don't have a clever way to remember this one. I tried to think of one, but basically, if you can remember rotenone's here, carbon monoxide cyanide is here, then it's kind of a process of elimination to remember that antimycin A then is at complex 3, and it's going to shut down complex 3. And then there's one more, oligomycin, which really isn't used too much in clinical practice. That's at complex 5. Oligomycin, and that's going to inhibit, remember complex 5 is the ATP synthase, so it's going to inhibit and shut that down. And then other drugs, you may hear a term uncouplers, electron uncouplers, or proton uncouplers, or however you do, basically uncouplers. All that uncouplers do, and there's a broad classification of these various drugs. I'll name a couple of them. Aspirin, alcohol. There's one called dinitrophenol, DNP. So these are kind of like 3 main ones. These are called electron uncouplers. All they do is this membrane that we're talking about, that all of these complexes are embedded in. Remember, the membrane is called the inner membrane. It's basically destroying the membrane. So it's basically making holes throughout various parts of the membrane, so that now all of those protons and things that we have collected over here, they can now just go right through, so that when you get to the final step at complex 5, you have no protons to generate the energy to produce the ATP. So those are uncouplers. Really high doses of aspirin acts as an uncoupler. Alcohol is an uncoupler, a lot of alcohol, if you drink a lot of alcohol, and then dinitrophenol is also an uncoupler. Now, it's important to know this. You will still generate heat. Let me show you what I mean. When protons are just flying through the membrane, it doesn't mean that any of these complexes aren't working. It just means that when you get to the final complex, you don't have the force to generate the ATP. So you've basically wasted all of your caloric energy going through all of these complexes to have no good end result. Only thing you're generating all this, you're not making any ATP. All you're really generating is excess heat. So whenever a person takes uncouplers in really high doses, they will radiate tons of heat. They'll get really hot. I don't know if you ever drank a lot of alcohol, and then you go to lay down that night, and if you drank enough alcohol, you'll be extremely hot that night. You probably won't be using covers. You'll just be feeling really, really hot and sweaty. That's because alcohol is an uncoupler, okay? So now we've covered the drugs, and I want to cover one more little thing, which is kind of towards the beginning again. Just remember we talked about coenzyme Q. Know that another name for coenzyme Q is ubiquinone. Ubiquinone. That's easy to remember because remember, coenzyme Q is involved with complex 1 and complex 2 to take all the electrons to complex 3. And I just remember that because coenzyme Q starts working at the very first complex, U is for uno. And uno means 1. So it just means 1. And that helps me to remember, okay, this is another name for coenzyme Q. And then also, one more thing about complex 1, and then we'll wrap up the video. FMN, flavin mononucleotide. Remember, that comes from riboflavin, which is one of your vitamins, your B vitamins. Flavin mononucleotide and iron sulfate are both needed as cofactors in complex 1 involving coenzyme Q. That's really important. If you don't have flavin mononucleotide or you don't have iron sulfate, then you cannot operate complex 1 in the correct way. Therefore, coenzyme Q won't be able to transport the electrons from complex 1. How do you remember that? Back to our funny little mnemonics. There's an F at the beginning of both of these. F stands for first. So it's affecting at the first complex, complex 1 involving coenzyme Q. Okay, so I hope this video helped. I think I've covered like the major parts of the electron transport chain. I know I didn't go exactly step by step through every little part, but I think that these are the parts that a lot of times board exams will ask you, and it's really easy to miss questions on them because you may have learned it before and everything made sense, but it's just remembering the part. For example, the names of the complexes or the names of the drugs or where the drugs work. So I hope all of my little goofy mnemonics helped you to remember all of this. If it helps you in any sort of way, leave a like, comment, let me know if you want to add anything, if I could improve anything. Please subscribe to the channel, and I will see you in another video. Bye, guys.